Hello, everyone. Today, we are very excited to present our paper, Selected Functions of Range Queries are Learnable. This is the outline of our presentation today, and let me start with some background knowledge. Selectivity estimation is a core problem in the query optimization pipeline and has a rich history of research over many decades. A selection query is a predict that selects a subset of tuples from the database, and the selectivity is defined as the probability that a randomly chosen tuple from the database satisfies the predict. In recent years, the main thrust in this area of research has been in developing machine learning models and algorithms, often using deep learning techniques that empirically outperform existing methods in real-world DB systems. Those empirical achievements motivate us to think about the theoretical reason behind them. Why is a selectivity estimation problem learnable? In this paper, we establish a learning theoretical framework showing that the selectivity estimation is indeed learnable from a small set of training queries. Let's first formalize this problem. Suppose we are given a range space, which is defined by a universe of data points and a set of ranges. Each range is a subset of data points, and the selectivity function associated with the data distribution D over X is a real value function from the range space to a real value between 0 and 1. And the selectivity of a range query is the probability that a randomly chosen data point from D satisfies the query. Then the question is, without access to the underlying data, can we learn the selectivity for a new query just by observing previous queries and their selectivities in the workload? In order to learn a selectivity function, we employ the agnostic learning framework for real value functions. We define the set of distributions over X, the family of selectivity functions, and the set of input instances while training samples are drawn. Now, given a training set of n samples drawn from a distribution over Z, an epsilon delta learner will output a function such that for any distribution over Z, the error achieved by this output function is at most epsilon larger than the error achieved by the best selective function from this family with probability at least 1 minus delta. Intuitively, the family of selectivity functions is epsilon learnable if there exists an epsilon delta learner for every value of delta. And our main theorem states that the family of selective functions is learnable if the range space has a bounded VC dimension. The VC dimension of the range space is defined as the maximum size of data points that can be sheltered by the range space. The classical packed learning theory says that a Boolean function is learnable if its VC dimension is bounded. Generalizing this notion, it has been shown that a real value function is learnable if its fat sheltering dimension is bounded. This reduces the question of the learnability of selectivity function to bounding their respective fat sheltering dimensions. And our main result shows that if a class of selection queries has a bounded VC dimension, then the fat sheltering dimension of the corresponding selectivity function must also be bounded, and therefore the selective function of such queries is learnable. This result has several implications for important queries in practice. For example, the orthogonal range queries. Take a geometric view, each tuple is a d-dimensional point and each query is a d-dimensional hyperrectangle. This range space has a bounded VC dimension, so their selective function is learnable. The second example is the linear inequality queries, which allow multiple attributes to be brought together into one linear inequality. As earlier, each query is a d-dimensional half-space, and using known bounds on the VC dimension of half-spaces, we know that the selective function is learnable. The third example is the distance-based query, which specifies a reference object and finds all objects that are within some distance from it. As before, each query is a d-dimensional L2 ball, and invoking the standard bound on the VC dimension of L2 balls, the corresponding selective function is also learnable. There are some other classes of queries that have infinite VC dimensions, so their selective functions are not learnable from our theory. For example, the convex polygon queries with arbitrary number of vertices. But it should be noted that our framework does not rule out the possibility of other learning theories for range spaces with infinite visit dimension, which is left as an interesting open question.
While our theory establishes the learnability of the selectivity of range space with bounded VZ dimensions, it does not by itself prescribe any specific model or learning algorithm. So we also need a procedure that, given a set of training samples and a family of data distributions, constructs a data distributions from the given family that best fits the training samples. Here, our goal is to describe a simple and generic framework, and we do not attempt to optimize the learning procedure for specific selectivity queries. Generally, the model of this framework is a collection of weighted geometric objects, and each of them has an associative weight indicating the data density inside the corresponding space. The weights are summed up to 1, and each of them is a real value between 0 and 1. Our estimation function is a mapping from a range to a real value between 0 and 1 in terms of a linear combinations of the weights of buckets. The algorithm to learn or train the estimator proceeds in 2 phases. The first phase, called bucket design, construct the sets of geometric objects, and the second phase is to assign the weights to the buckets to minimize empirical risk. The first model is CROHIST, namely a combination of a CRO tree and histogram. The buckets used by CROHIST are a set of disjoint cells in the partition on the data space by a CRO tree. Remember that we do not have access to the underlying data, so the construction of CRO tree is guided by both the geometry of training queries and their selectivity. We do the split by expanding the CRO tree layer by layer from top to the bottom. We use each range R from the training sample to expand the CRO tree, and we always start from the root, which represents the whole domain space, and then with one node each time. Suppose node U is visited right now. If the density of the intersection between U and R is larger than some predefined threshold, we split U into 4 equal-sized nodes and apply this procedure recursively to each trial of U. Otherwise, we just stop splitting U. This example shows the update by applying this blue rectangle to split the CRO tree. After computing weights for bucket in the training procedure, the next question is how to use this model to predicate selectivity for a new query. Suppose our model consists of a k buckets. Our estimator is a linear combination of k values, each of which is the density estimation on the intersection between a bucket and the new query. We adopt the assumption that the data distribution inside each bucket is uniform, so the density is proportional to the volume of intersection. Our second model is pointed. Instead of using orthogonal ranges as buckets, pointed use a collection of points. Remember that we do not have access to the underlying data. So to get these representative points, we sample them from the training ranges with sampling size proportional to the selectivity. In addition, we sample a small number of points from the whole space in case training ranges do not cover some regions. So how to use this model to predicate selectivity for a new query? We use an indicator function to check whether each bucket is included in the query range R or not, and the selectivity estimation is the sum of weights of the bucket within range R. Here is a visualization of the data distribution modeled by these 2 methods. The left figure is the underlying data distribution, which we don't have access to. We can see that both methods can roughly capture the underlying data distribution. As a brief summary, the partition The partitioning of queries is sensitive to both the query and data distribution and irrelevant to the ordering of the training set. But it is difficult to scale to high dimension or other types of query since we need to compute the volume of range or their intersection. On the other hand, pointed scale well for high dimension and more complex geometry objects, but it is not that accurate as queries, and the performance heavily depends on sampled points.
And thus, let me share some experiment results. We use real-world datasets and studied 3 different classes of queries, which are the orthogonal range queries, half-space queries, and bulk queries. For each class of queries, we generate 3 different workloads by varying the distribution of their centers. For example, data-driven, random, and Gaussian. We adopt 2 common error measures for evaluation. Root mean square error is the L2 norm error between the true cardinality and the estimator. Q error is the absolute quotient of estimated and true cardinality. For fair comparison, we select methods that only have access to query workload, but not the underlying data, and Isomar and Quicksell stand out from literature for handling range queries. To verify our theory, we ask the first question: how does the training size affect the performance of the learned model? Our theory has shown a clear dependency between error epsilon and the training size m. We now explore this dependency empirically. This figure shows the quantities for data-driven workload over power data. We vary the number of training queries, and each line plot corresponds to a specifically sized training set. As we can see, error generally decreases with model complexity, although it eventually flattens out, and in one case, even trends up because of overfitting. As we increase the number of training queries, error decreases, although the rate of decrease also diminishes, consistent with our theoretical prediction. The good news is, with 200 training queries and 500 buckets, Qualtrics already offers acceptable accuracy with RMS error smaller than 0.02. Then we bring Quicksell and Isomar into the picture by fixing the model complexity for fair comparison. Isomar is the most accurate, but is much slower than the others. Other methods have similar training times since their model complexities are comparable. The second question is how the query distribution in connection with the underlying data distribution affect accuracy of the learned model. We replace the data-driven query workload with random and Gaussian, respectively. Here we show the prediction errors of different models with a workload from random distribution. We use the same setup on power data as earlier. Overall, we have similar observations. Selectivity is still learnable even if query distribution is independent of data. Our next question is, what if training and testing query distributions do not match? The learning theory will not provide us with any guarantee on the performance, but in practice, if the text query workload is not completely disjoint from the training query workload, we should still expect to gain something from a learned model. We use a 2D Gaussian query workloads, but shift the Gaussian distribution by different location of the mean center. We can see that when the training and test query workloads are the same, the error is the smallest in most cases. If we fix the training query workload, the error will gradually increase with the test query workload shifting away. Similarly, if we fix the test query workload, even when the shift is large, there is still overlap between their coverage of the underlying data space, so the error remains manageable. Our next question is, how does the dimensionality of data space affect the learned model? For all these queries, we see an exponential dependency of sampling complexity on dimension D. Pointcase is our method of choice in higher dimensions. For each line plot, we see that the error gradually decreases with more training queries and eventually flattens out. As we increase D, we see the series of line plots pushing away from origin. The last question is, how does the query type affect the learned model? We are interested in half-space and bulk queries, which have many applications in databases but have seen less work on selectivity estimation. According to our theory, selectivity for these queries are also learnable. We only show the results on Qualtrics for 2D, since it does not scale well to higher dimensions. We can see that error generally decreases as we increase the training size, and higher dimensionalities generally requires a bigger training size to achieve the same level of accuracy.
As a brief summary, we establish a formal framework for applying machine learning theory to DB problems and give a generalization bound for selective de-estimation problem. And we design two simple algorithms with a genomic model to verify our learning theory, which also match or even perform better than the state-of-art methods. There are many interesting open questions. As machine learning for DB advances further, we hope that the formal length we introduce in this work can be generalized and adapted to a broad class of DB problems. Thank you for your listening.